In many instances, no or insufficient data are available to fit a log-normal distribution. In these cases, experts are leaned upon to estimate the minimum, the most likely, and the maximum values using what meager data exists, analog data sets, and intuition. From the estimated min, most likely, and max values, a triangle or beta distribution can be constructed, and subsequently, mu and sigma can be calculated. Namely, extraction of the mean, median, and variance from the beta distribution can be used to calculate mu and sigma using the 3-point or LSS methods that was demonstrated in the previous video. Because of insufficient data, the scatterplot slope-intercept technique can't be used. I found the beta distribution preferable to the triangle distribution in Excel for two reasons. One, beta's dispersion can be modified using lambda, and two, Excel conveniently has a built-in beta function. Alternatively, a triangle or beta distribution alone may be suitable for your analysis and can be used directly without calculating a log-normal distribution. In this slide's example, the experts estimated the min, most likely, and max inputs, and then calculated a beta distribution with a lambda of 30 using 5,000 samples. Then mu and sigma were calculated using the 3-point and LSS formulas with the extracted mean, median, and variance from the beta distribution. Visual inspection of the charts, the PDFs above and the box and whisker plot below suggest no practical difference between the 3-point and LSS methods. The resulting table supports this finding. The mean, the mode, and the P50 or medium are similar, as is the interquartile range. Some disparity in the min and the max values are noted, but this can vary from simulation to simulation. However, the P05 and P95, approximated by the whiskers on the box and whisker plot, are similar, and the outliers representing less than 5% of the population. Running more samples in this example's distribution would tend to increase the max value and approach the assigned input of 238,050. So now let's move on to the Excel demonstration. Let's say you're asked to provide a distribution of oil field sizes in a remote region of Africa where no exploration has been done. You're also asked what's the potential amount of oil contained in the 30 anticlinal structures identified, namely 30 times the average field size. Based on the geology of the region and your experience in other parts of the world, most of the fields should be around 3,700,000 barrels of oil, KBO, log-normally distributed with a minimum of 300 KBO and a maximum of 100,000 KBO. This Excel worksheet shows how to solve for the field size distribution, or any log-normal distribution for that matter. Firstly, consider that determining the log-normal parameters, mu and sigma, from only the min, most likely, and max inputs is not intuitive. So the question arises, how do you determine mu and sigma? I found that a beta distribution can be easily calculated in Excel, from which the mean, standard deviation, and variance can be calculated, which provide a pathway to the log-normal parameters mu and sigma. And the mean, standard deviation, and variance from the beta distribution can be plugged into the 3-point or LSS models for calculating mu and sigma. With data ranging over many orders of magnitude, in this worksheet's example, the differences in the resulting log-normal distribution from using the different methods is not significant. The results can vary depending on the beta's dispersion factor lambda. The question is, which method is better? None of the methods exactly match the input parameters, as we can see by examining the statistical results. So, what's more important? Matching the most likely, the max, the min, or the interquartile range? Perhaps achieving some expected mean or P50 is the more important question. Let's play around with the dispersion parameters and watch the differences. Let's start off by looking at a lambda of 3. When we examine the PDFs, we see that the LSS method in blue looks askew relative to the 3-point in orange or the beta in black, When we look at the box and whisker plots, we notice that the max value for the 3-point ranges up to 700,000, which is significantly greater than our input value of 100,000. But at this scale here, it's hard to tell what's going on. So let's change this scale and take a closer look at the interquartile range. Now that we've changed the vertical scale of our box and whisker plot, we can see that the difference between the curves are also quite a bit different, but not bad considering the large order of magnitudes that the data spans. Notice that the means look fairly similar. Let's take a closer look at the statistical results. We see that the means look very close. The mode for the beta and the 3-point system look very close. The LSS method is a little bit high. The minimum is also high for the LSS method. And we can see that there's quite a bit of difference in the max values. So with a lambda of 3, I would think that either the 3-point or the beta would do a good job of modeling our distribution. Let's take a moment and calculate the estimated amount of oil that we'll find. So we'll put in a calculation here, which would be the number of fields times the mean value for the 3-point. And we'll do it for the other two. And as we can see that the difference between the estimated amounts of oil are somewhere around 640 to 650,000 barrels of oil. So, which isn't really a big difference. So let's see what a change in lambda will do. So instead of 3, let's do this at 30 and shift F9. And what we see is that the curves now have pretty much aligned. And still we have this limited scale here on the box and whisker plots, and everything looks fairly similar. So we're really compressing it. Let's take a look here at the mean values. We can see they're much smaller. Before they were in the tens of thousands. Now we're around 6, but all the means look fairly close. The modes look close. The minimum values are close to our inputs of about 300. And our maxes are all much smaller than our input here of 100,000. The IQRs are also much smaller. And the mean amount of oil is somewhere around 200,000 barrels now, where before it was around 650,000. So significant difference in the outcome of our estimated amount of oil based on the dispersion factor that we use. Down below in the spreadsheet, I have a figure here that kind of shows the difference between a lambda of 330, where you can see these differences. And I've kind of outlined here for the mean, the IQRs are much different, as well as the P50s. So my recommendations are: 1, use a beta or a truncated 3-point distribution and adjust lambda for the appropriate amount of dispersion, or IQR, and a max. Also, use a lambda that meets your expectations for the mean value. Use a smaller lambda with greater uncertainty of the distribution. Just a couple of last notes about the workbook. I'll scroll back over here on the left, and let's change this back to 3. And I'll change the scale back to where it was, and make the point that when we see these long distributions on the log normal, we can also truncate this, which will probably be the most reliable answer. And in the next demonstration, I'll show how to truncate the curve. If you want to dig more deeply into how all these things are calculated, you can just click on the cells and look at the formulas in the formula bar. Most of the work is done over here on the right, where here's my random numbers, and then I calculate the distributions here. Again, just click on the cells and you can find the formulas. This small table here is just used for plotting, where I just use the probabilities and then do the calculations, which makes it much simpler to make the PDF plots. Also, I've done some write-ups here that show the different formulas that are used and my notes about what this all means. If you want to get more information, download the Excel file. You'll find a link in the video description. Thank you for listening. Like and subscribe.